Hello everyone, this is Vasanth, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to discuss shear stress variation in I-beams. So these I-beams are generally widely used in civil engineering. So if you see the I-beam, it will look something like this, right? So if you take the I cross section and it is having some shear force V, then the shear stress will be in the direction of the V in vertically, right? So that will be something like this. And apart from that, there will be horizontal shear stresses in flanges. So these are flanges, okay? These upper ones are flanges, okay? This middle portion is known as wave. So whatever formula tau is equals to VQ by IT, this formula assumes that the shear stress variation across the width is constant, right? Means we will assume the same shear vertical shear stress across width. But if the width is more, the actual shear stress variation will be not uniform. So then this result will not be accurate, right? So generally, this formula will not give accurate result in flanges, okay? But it will give accurate results in web. But if nothing is mentioned, we can use in flanges also. But in general case, it is only valid for web. Means it will give somewhat accurate results in web, okay? The error will be less in case of web. So let us solve. So shear stress in web. So let us take a point at a distance y1 from the neutral axis. See, neutral axis will be at the centroid. So this is the centroid of I-beam. So this will be neutral axis, right? So for calculation of Q, we will consider this one. So this, let us say this part as 1, 2, this part as 1, okay? So for this one, the area will be this thickness. This width is B and this thickness is given by H minus H1 by 2 divided by 2, right? So because this is H and this will be H by 2, right? So that will be, this will be H by 2, there will be no 2. So the area will be B into H by 2 minus H1 by 2. For this one, that will be, this is Y1, so this will be H1 by 2 minus Y1. So the area will be T into H by 2 minus Y1 because the thickness is T, right? So Q will be is equals to Q1 plus Q2, right? So this will be A1 Y1 dash, this will be A2 Y2 dash. So Q will be is equals to A1 is B into H by 2 minus H1 by 2, right? And Y1 dash, that will be centroid of this one, the distance of centroid of this area from neutral axis. So that will be at a distance H by 2, H1 by 2 plus H by 2 minus H1 by 2 divided by 2, okay? So this will be Q1 and Q2 will be T into H1 by 2 minus Y1 and into centroid distance from neutral axis. So that will be over here. So this is Y1 and this will be H1 by 2 minus Y1 by 2. So that will be is equals to Y1 plus H1 by 2 minus Y1 divided by 2, right? So we will get Q is equals to B into H by 2 minus H1 by 2 plus this will be H1, into, that will be H1 plus H divided by 4, right? Plus T into H1 minus 2 Y1 divided by 2 into this will be Y1 by 2, so H1 by 4. So that will be H1 minus plus 2Y1 divided by 4. Okay. So if we calculate this one, if we write this one, Q is equals to B divided by 8, H minus H1 into H plus H1, right? Plus T divided by 8, H1 minus 2Y1 into H1 plus 2Y1. So that we can write as like this, B by 8 into H square minus H1 square plus T by 8 into H1 square minus 4Y1 square. See, the only variation will be of Y, right? All this H1, T, H and B are constant for a given I beam. Only the variation will be with respect to y, right? So we know that tau is equals to VQ divided by IT. So the I is for whole cross section. So this will be constant for given I beam. Per web, this is constant per web, right? And V is also constant. So the only variation will be Q, right? So we can write V by 8 IT into this thing. So I, we can calculate the I. How you will calculate the I? See, this is something like this, and this one, right? So see, we can say iska I plus 2 into iska I about neutral axis. So iska I we can write as what is the distance that one will be h1, right? So we can write it as b h1 cube divided by 12, right? Plus 2 into iska I. So we can calculate that I. How will you calculate that I? See, for that thing, this is the section and this is the centroid. So this thickness will be there, and so we can say that this will be the length, right? So suppose this thickness is some d, then we can write for this at centroid will be bd cube by 12. But we need to find out at this position that will be from a distance some d dash. Okay, then we can write I dash will be is equals to bd cube by 12 plus area of that flange into d square, right? D dash square. So this into 2, if we calculate, we will get something like this, okay, that you can calculate. So this is the variation of shear stress. So see, the only value which will vary along the depth is y, right? So it will change with y. So when it will be maximum, because this is negative, it will be maximum when y1 is equals to 0, means at neutral axis, right? And when it will be minimum, see, we are calculating for the wave, right? So for the wave, the y will be maximum at this position, that will be at h1 divided by 2. So that will be shear stress will be minimum when y is equals to plus or minus h1 by 2. Okay, so at the interface between the flange and the wave. So this is the tau minimum and this is tau minimum and this is tau maximum, and we know that this is parabolic variation, right? So if we draw the diagram, it will look something like this. Here it is minimum, and see, it is symmetrical about this neutral axis. So whatever shear stress value over here, that will be same shear stress value at over here with same distance y, at same distance y. Okay, so here it will be tau minimum, and here again it will be tau minimum, and here it is tau maximum, and the variation is parabolic. So we can draw something like this. So this is shear stress variation in the web, right? So what is the shear force, net shear force in the wave? So how much shear force is resisted by this wave? So that will be is equals to V wave will be is equals to integral tau dA, right? Wave, right? So means this tau dA will be the area of shear stress variation diagram into thickness, right? So this thickness is T. So now we need to find out the area of shear stress diagram. So it comprises of one triangle, rectangle, and this parabola, right? So rectangle ka area, see, let us write T into rectangle ka area will be that will be tau minimum, right? This is tau minimum and this is h1, so that will be tau minimum into h1 plus parabola ka area. So if you take the parabola, that is something like this, right? So iska this distance is tau max minus tau minimum, right? And this distance is h1. So we know that that area will be given by 2 by 3 into this h1 into this length, that is 2 max minus tau minimum. So let us write that. So 2 by 3 h1 into tau max minus tau minimum. Okay. So this will give us T h1 divided by 3 into 2 tau max plus tau minimum. So this will be shear stress resisted by the, shear force resisted by the wave. I hope you understood. So if you see, the variation is parabolic. Okay. Remember this point, the variation is parabolic, and the variation is parabolic in rectangular case also. Okay. I hope you understood the shear stress variation in wave, right? So see, if we need to calculate with the same formula in flange also, so then here it will be 0, right? And here it will be 0. So it will be 0 over here, and if you take this one, it will be 0 over here. If you take this one, it will be 0 over here. And see, if you take the shear stress over here, just before this one, the thickness will be this, that will be B. Just after this interface, the thickness will be T. So that means here the shear stress will be minimum compared to here, right? So that means it will go something like this. So if you draw the diagram, that will look like this, like this, a straight line, and like this, a straight line, and like this. Okay. So this will be the shear stress variation with this formula. Okay. In the IB. I hope you understood this concept clearly. If you like this lecture, do subscribe to our channel 9 Point. Thank you.